Hello people, I'm Bharat Acharya. Welcome to our new video. So in today's video we're going to learn this chip called 8255. 8255 is called Programmable Peripheral Interface. So it provides an interface between the processor and I/O devices. Now let me just first give you an introduction what this chip is so that you get the basic idea, and then we will learn the architecture, the designing and I/O command, BSR command, all of that. Okay, first let's just get a brief idea. Okay, it's a very simple chip. Now, this is your MUPI, your processor. And the good thing about learning 8255 is, it is the same whether you're learning it for 8085 or 8086. This whole video applies to both processors equally. There's only one line that will change in designing between 8085 and 8086. I'll tell you the change. Otherwise, the same. So even if you're a student of 8085, this whole video applies to you. Okay, look here. This is your MUPI, let's say 8086. This is some I/O device. What are I/O devices? Keyboard, mouse, printer, monitor, etc. Now tell me, at home, do you connect these I/O devices directly to the data bus of the MUPI? No, obviously not. You connect them to what? Ports. You know, on the front side, back side, on the sides of your computer there are ports, correct? Now, where do these ports come from? These ports come from a chip like 8255. Why do you need these ports? Why can't we connect the I/O device directly to the processor? Can we? Of course we can. Remove 8255. You can connect this directly to the data bus of the processor. What's the problem? When you do transfers like this without 8255, it's not that the transfer cannot happen. Of course it can happen. But the transfer is unreliable. Why? If the I/O device wants to send data to the processor, to MUPI, does it ask for any permission? Tell me, in all these lectures you see in all my videos so far, have I ever used the word permission? No, because there is no such signal in the MUPI. I/O device blindly sends data to the MUPI, hoping that MUPI will be in a position to accept the data, which it will be, of course, but maybe it's not. Maybe at that time some other interrupt comes which is higher priority, maybe some bus request has occurred, God knows something goes wrong. Does the MUPI give any acknowledgement saying that it has received the data? No. So there was no permission taken, there was no acknowledgement given. That means nobody knows for sure whether this transfer had actually completed or not. That's why it's called unreliable. Now, we don't want such unreliable transfers. When you put a pen drive in your computer and you transfer a song, you believe it has been transferred. You don't get up thinking maybe it was transferred, maybe it was not. You need more reliability. And that reliability comes by putting an 8255 or something like an 8255. It doesn't have to be hard and fast this chip. Basically the same concept. Now look here. 8255 on one side is connected to the processor using the data bus. On the other side, it is connected to I/O devices on ports. 8255 has 3 ports. Port A, Port B, Port C. All ports are 8-bit ports, which means you can transfer 8-bit data. All ports are bidirectional. That means they can be used as input ports or as output ports. You understand that? Now, suppose an I/O device wants to send data to the processor. I/O device will first send data to 8255. How? Blindly? No. I/O device will ask for permission. Something that you cannot do with the processor, with MUPI, but you can do with 8255, because 8255 is created for doing this. So it has signals that supports all this. So I/O device will ask for permission. 8255 will give permission. Data will come inside 8255 and will get stored into a temporary register. Now, 8255 will inform the processor that it has data. Whenever free, processor will give a read signal and ask for data. The question is, suppose right now the processor is not free. Suppose something has gone wrong with the processor, it's busy doing something else. In the meantime, if the I/O device sends a new number like 5, that 5 will overwrite on 3 and 3 will get lost. Should that happen? No. Will that happen? No way. Why? Because before sending the next number also, I/O device will have to, yes, you got it. I/O device will have to also again ask for permission. This time will 8255 give permission? No. When will it give permission? Only after 3 has been transferred to the processor. Can that take time? Yes. Can that take a long time? Yes. 8255 doesn't care about time because it doesn't know time. Time in computer systems is clock pulse. See, you and I are living objects. We understand time is passing. From now till now, time passed. You and I understand that. But a processor or chips don't understand that. They are not living objects. For them, time is clock pulses. They count clock pulses and that's how they understand how much time has passed. In 8255, come on, look here. In the whole architecture of 8255, there is no clock. What does that mean? That means 8255 doesn't understand time. That means it doesn't care how long the processor takes to get the data. till the time the processor doesn't ask for the data and take the data, till the time 8255 will not give permission for the next data. That means no matter what happens, you will not lose the number 3. And 3 is just symbolic. That means any number, any data transferred in the system will not be lost. I hope you got a basic idea what we are learning. Of course, don't think you learned it all. I've just given an introduction. Now I'm going to explain all of this in full detail. By the time you finish 8255, you'll know all of this in full detail with timing diagrams, etc. Okay? Now look here. These signals which made the transfer so reliable are called handshake signals. And this method of data transfer is called handshaking. So in one line, the reason why we use 8255 is because it can perform handshaking. And that's how the transfers become more reliable. Tell me, did you understand this basic introduction? Now, let's start running the chip. Come on. Sorry. I hope you've seen the 8259 video and all other videos before this. So then if you have seen all that, you'll find this architecture super simple. Look here, even if you've not seen 8259, please check it out. Again, if you're an 8085 student also, practically the whole working of 8259 is the same, whether it works with 8085 or 8086. The only difference is in 8086 there are 2 INTA bars, and in 8085 there are 3 INTA bars. That's the only difference. Anyway, let's not get into that. Now look here, this is your 8255 architecture. So this is 8255. What have I made you understand? What do you know? 8255 is between whom and whom. What is here? The MUP, the processor. Connected on which bus? Data bus. Good. On this side, we have I/O devices connected on ports. Okay, these are ports. What do you know? There are how many ports? Yeah, there are 3 ports. So there is port A, port B, and port C. Port A, all ports are 8-bit ports. Port A is 8 lines are called port A 0 to port A 7. Similarly, port B again 0 to 7. Port C is also an 8-bit port, though it's divided into 2 parts. Port C 0 to 3 is 4 lines. Port C 4 to 7 again 4, 5, 6, 7 are again 4 lines. So these are 2 parts of port C. This is called port C upper because these are the higher 4 lines of port C, and this is called port C lower because they are the lower 4 lines. I'm sure you're wondering why is port C divided into 2 parts. Don't worry, you'll understand. Just give it some time. This division is not some physical division. It's just logically shown like this. Physically, it is also one port, just like port A and port B. And to all the ports, you can connect devices and transfer data. So let's say to port A, we have connected a device. Give me an example of a device. Yeah, something like okay. So on port A, we have connected a printer. On port B, let's say we have connected something like say something, whatever device comes to your mind. Yeah. So on port B, we have connected a monitor. Okay. On port C, let's say we have connected some device, something like a speaker. Purposely, I am taking all output devices because I want to make you understand out as an example. So this is the printer, this is the monitor, this is the speaker. So this is how you print, this is how you display on the screen, this is how you listen to music. Now, this is your MUP, your processor. Okay, look here. Suppose the MUP wants to send data to the printer. You want to print something. MUP will send data to 8255. That data will enter 8255 through the data bus. Are you clear? Once it comes inside, should it go out on all ports or one port? You tell me. Of course, it should go out on one port. Everything that you watch on the monitor should not get printed. Everything that you print should not be coming on the monitor. Each port is a different port. So, when you send data to port A, it should go to port A. When you send data to port B, it should go to port B. And same goes with port C. That means port A, port B, and port C must have their own unique address. Please tell me, did you understand this? 8255 is one chip, but it has several addresses. It needs several addresses. It needs an address for port A, another address for port B, another address for port C, and one more address for the control word. Understand what I'm saying? There is something called a control word. What do you send to the ports? Data that you want to print, you want to display, etc. What do you send to the control word? This is the control word. This is port A, this is port B, this is port C, this is the control word. What do you send to the control word? Command. Say again what? Command. So there are commands that you send to 8255. There are 2 commands. IO command and BSR command. I'll be teaching you both commands in this video itself after the architecture. But my point is, why do you send commands? By sending commands, you initialize the chip. You decide how the chip should work. You decide how you want to program the chip, because 8255 is a programmable peripheral interface. The word programmable means you can set it up the way you like. You can make the ports behave the way you want them to behave. And for that you need to send commands. Now you tell me, when you send a command, that command also will be sent, when I say you, I mean the MUPI. So the command will also be sent by the MUPI through the very same data bus. But should it go and get printed? No. Should it go to the monitor? No. Should it go to the speaker? No. That means you need another address, a fourth address, which is for the control word. Tell me, did you understand? So let me just simplify it. Okay, look here. I hope you can see this clearly. Okay, look here. So this is 8255. This is its data bus. Through this data bus, what do you send? You can either send data which will go to port A, or to port B, or to port C, or you may send a command which will go to the control word. Please tell me, did you understand? So what do you understand? Anything that comes in through the data bus has 4 places to go. Now who decides where it will go? That is decided by these 2 lines, A1 and A0. A1 and A0 first of all are 2 lines. 2 lines will give you how many options? 4. So if A1, A0 are 0, 0, port A will be selected. If they are 0, 1, port B will be selected. 1, 0, port C, 1, 1, control word. Tell me, did you understand? Did you understand this? A1, A0 are a part of which bus? Guess. A1, A0, A. They are a part of address bus. These 2 lines, as they change, they produce 4 different options, which means they produce 4 different addresses. You understand, as address lines change, that means you got a new address. So there are 4 addresses for 8255. 1 address for port A, 1 for port B, 1 for port C, 1 for control word. Once again, anything that comes in through the data bus has 4 places to go. If A1, A0 are 0, 0, it will go to port A, or if they are 0, 1 to port B, or to port C, or to control word. Tell me, did you understand this? Now, to this A1 and A0, the MUPI will connect A1 and A2. That is if you are working with 8086. If you are working with 8085, it will be A0 and A1. So to A0 you connect A0, to A1 you connect A1. But if you are working with 8086, I hope you have seen 8259 designing video. Please watch it. In that video, I've taken 1 whole hour to make you understand designing. Here I am not doing the whole process again because it's not required. Once you know designing for one chip, you know it for all chips. The concept is the same. So in 8086, we never give A0 inside any chip. Why? Because we don't want consecutive addresses. We want alternate addresses. Look here. This is A0 to A7. We need some address for 8255. Let's say 8255 is at the address 80. The binary form of 80 is 10000000. What does that mean? When the processor gives address 80, this is the binary pattern that will appear on the address bus. Tell me, did you understand this? Now, the lines which are going inside to decide these 4 options are A2 and A1. These are A2 and A1. If they are 0, 0, port A will be selected. If they are 0, 1, port B. 1, 0, port C. 1, 1, control word. That means these 2 lines are used for internal selection. This is internal selection. Internal selection. The remaining address lines will do chip selection. And A0, the reason why we didn't give A0 inside is because if we had given A0, A1, then these 2 lines would have changed. So the addresses formed would have been 80, 81, 82, 83. That is good for 8085. But if you're working with 8086, you don't want consecutive addresses. You want alternate addresses. You want one chip to have only even addresses, so that in future we put one more 8255 at the corresponding odd addresses 81, 83, 85, 87, so that MUPI can read from 80 and 81 together, 82 and 83 together. This concept is called banking. I've already explained this in 8259 designing. Please check out that video. So the addresses of this chip are 80, 82, 84, 86. 80 is the address of port A, 82 is the address of port B, 84 is the address of port C, and 86 is the address of the control board. Are you clear? Now let's do the decoding for this chip. The decoding means only for these 4 addresses this chip should be selected, for no other address. So for that we take a 3:8 decoder. Everybody knows this, we have seen it in designing. We take 3 lines, A7, A6, A5. This is A7, A6, A5. What does that mean? What does all this mean? Whenever processor generates an address A0 to A7, out of those I have picked up A7, A6, A5 and I have given it to the decoder. I have told the decoder only for these 4 addresses this chip should be selected. Now for these 4 addresses, A7, A6, A5 will have the pattern 100. 100 on the inputs of the decoder will activate Y4 output. Decoder has 8 outputs. If they were 000, Y0 would be activated. 001, Y1. Similarly, blah blah blah. 100, Y4 will be activated. When it is activated, it is 0. Are you clear? That is combined with A0 signal. A0 also has to be 0. So what am I saying? Only when Y4 is 0 and A0 is 0. Only when both of them are 0, answer should be 0. So the gate we use is OR gate. OR gate gives a 0 strictly only when both are 0. So the answer will be 0 and that will produce the chip select signal. So the other way to understand it is chip select is an active low signal. It wants a 0. This chip will only be selected when Y4 is 0 as well as A0 is 0. Y4 is 0 means A7, A6, A5 are 100 signal. So I have put these 3 conditions and I have put this condition. Moreover, A4 and A3 should also be 00. In a decoder, there are 2 active low enables, G2A bar and G2B bar. They need 0. If I connect A4, A3, I have put the condition only when they are 0, the decoder will be enabled. Otherwise, the decoder will be disabled. So when the MUP gives any other address other than these bits will change. When these bits change, this chip will not be selected. This chip is now only going to be selected when A7 is 1, A6 is 0, A5 is 0, A4 is 0, A3 is 0 and A0 is 0. So these are the conditions I have put. What are the lines on which I have not put conditions? A2 and A1. They can be 00 or 01 or 10 or 11. So if all of these conditions are satisfied, changing only these 2 lines produces these 4 addresses. That means on these 4 addresses this chip will be selected, but on any other address it will not be selected. This is called designing. I hope you understood it. I went so fast because I've taught this whole thing in the 8259. No point repeating the same thing again. Please check out the 8259 video. But anyways, I've explained to you what this designing was. So now come back to this diagram and tell me. Excuse me. Anything coming in through the data bus can either go to port A or to port B or to port C or to the control word. This is the control word. Port A has the address 80. Port B has the address 82. Port C has the address 84. Control word has the address 86. Please tell me, did you understand this much? A1 and A0 to which we connect A2 and A1, they can be 00, 01, 10, 11. If they are 00, whatever comes will go to port A. If they are 01 to port B, to port C and to the controller. I think you understood this point. To read bar, write bar, we connect the IO read and the IO write signals from the processor. IO read and IO write because this is an IO device. To the reset, we connect the reset of the system, which if you are in 8086, if you've seen the minimum mode and maximum mode circuits, I'm sure. So there is a clock generator which gives clock reset ready. That same reset will be connected over here. And to the chip select, we make that circuit, that decoder that we just made, and we connect that decoder over here. So that's a whole interfacing, and this is the architecture. This is how the addresses are formed. Now the only thing left to be understood in this architecture, which I'm sure is still lingering in your mind somewhere, why is port C divided into 2 parts? You'll get the answer right now. Look here. 8255 operates in 3 different modes. There are 3 different modes of operation. Mode 0, Mode 1, Mode 2. They have names also. Mode 0 is called Simple IO. Mode 1 is called Handshake IO. Mode 2 is called Bidirectional handshake IO. I repeat the names: simple IO, handshake IO, bidirectional handshake. Now, there are 3 ports: port A, port B, port C. If you are in mode 0 called simple IO, all 3 ports are allowed to transfer data. That means you can connect a device on port A, port B and port C, each one of them, and transfer data. They are all available for data transfer. That is in mode 0. In mode 1, only port A and port B are allowed to transfer data. Port C lines are sacrificed to perform handshaking. Port C lines are sacrificed, they are lost to perform handshaking. Okay? Only port A, port B can transfer data. Now let's understand what this means. Do you remember, before this, I had shown a simple diagram showing handshaking. Do you remember that brief introductory diagram? In that, there were how many handshake signals? 4. 2 on this side of 8255, 2 on this side. So what do you understand? Any port which wants to do a handshaking kind of data transfer needs 4 additional lines for performing handshaking. I repeat, look here. In mode 0, which is called simple IO, mode 1 is called handshake IO. So it is very obvious that in mode 0 there is no handshaking. Since there is no handshaking, all 3 ports can transfer data. But in mode 1, when port A or port B works in mode 1, look here, port A is in mode 1, port B also is in mode 1. The port has 8 lines. Those 8 lines will transfer data, no doubt. But other than that, you need 4 additional lines to perform handshaking. 2 on this side of 8255, 2 on this side. So where do these lines come from? That permission, that acknowledgement that I told you about, they are not going to fly in air. You need lines to do that. So they are taken away from port C. So if port A is in mode 1, it will take the upper lines of port C to perform handshaking. Similarly, if port B is in mode 1, it will take the lower lines of port C to perform handshaking. Did you understand? If port A, port B both are in mode 0, they don't need any lines for handshaking, then port C is free to transfer data. But if port A, port B go into mode 1, they take away lines of port C to perform handshaking. Are you clear? That's why port C is shown as divided into 2 parts. This is called port C upper, which works with port A. So together it's called group A. Similarly, port C lower, which works with port B. So together they are called group B. Group A is controlled by the group A control logic. Group B is controlled by the group B control logic. Tell me, did you understand? Now, so that you could understand why port C is divided into 2 parts, I showed you this table. I have not explained the modes, I have just shown you the table. Now I can't leave an incomplete table because this will play in your mind. So I am just finishing the table, but don't try to go too deep into it right now. I have not taught it. When I teach you handshaking, you will understand this column more clearly. Right now I am just telling you what this column is. So in mode 1, port A, port B transfer data, port C is lost in doing handshaking. Mode 2, the more powerful version, bidirectional handshaking, input as well as output, bidirectional handshaking, that feature is given only to port A. Only port A can work in mode 2. Port B is still functional. It will work in mode 1 or mode 0, not mode 2. Mode 2 feature is only for port A. When port A is in mode 2, port B can be in mode 1 or mode 0. Port A is in mode 2, port B can be in mode 1 or mode 0. What about port C? As usual, lost in doing handshaking. Are you clear? I have not explained this. I just had to complete the table. I cannot give you an incomplete table, as I said. Then it will affect you. You will be thinking of this rather than thinking of what I am actually teaching you. So look here. Let me ask you this table in a different way. Which port can work in all the 3 modes? Which port can work in all the 3 modes? Port A. It can work in mode 0, mode 1, mode 2. Which port can work only in 2 modes? Port B can work only in mode 0 and mode 1. And port C can only work in mode 0. Otherwise, its lines are used for handshaking. Please tell me, did you understand? So that's your whole architecture. I hope you understood the architecture. Now we'll just move the camera on that side so that I can make you understand IO command and BSR command. Okay? Just a minute. Okay. So these are our two commands. They are called IO command and BSR command. Okay, now come on, tell me. What is the address of port A? 80. Port B is 82. Port C is 84. Control word is at 86. What do you send to the ports? Data. What do you send to the control word? Command. These are your two commands. IO command, BSR command. Since both are commands, both will be sent to the same address, 86. So if you are 8255 and I send you something at the address 86, you know for sure that it's a command because it has come at the address 86. But you still have a question whether it is IO command or BSR command because both are sent at the same address. So how do you know whether it's IO or BSR command? You look at the command. The MSB of the command identifies whether it is IO command or BSR command. This bit is called IO/BSR. If this bit is 1, that means you will treat it as this command, the IO command. And if this bit is 0, you will treat it as BSR command. Tell me, did you understand this? Look here again. I send you something at the address 86. You know for sure it's a command. You will look at the command. You will first look at the MSB of the command. If the MSB is 1, you will treat it as IO command, and the 0, you will treat it as BSR command. Tell me, did you understand this much? Now, we're going to start learning with IO command, finish it, go to BSR command. They're both very simple, but very important. Okay, there are a lot of papers where this itself is asked as a question, though it's super simple, but in the real world it has tremendous application. So because of that, they keep asking this. Now, first we're going to start with IO command. IO command is used to initialize 8255, to set it up. Now, what do you need to decide when you're initializing 8255? What do you need to decide? You need to decide two things for every port. You need to decide which mode it will work in and which direction it will work in. I repeat, the first thing you decide is the mode, and the second thing you decide is the direction. And you don't decide it globally for the whole 8255. You decide it for each port. So let's start. These two bits, first of all, because it's IO command, this bit will be 1. Tell me, did you understand? Now these two bits are used to decide the mode of port A. Why do you need 2 bits? 2 bits will give you 4 options. 1 bit will give you only 2 options. You know port A can work in 3 modes. Mode 0, mode 1, mode 2. So do you understand? You want 3 options. If you use only 1 bit, it would give you only 2 options, 0 or 1. You need 3 options, so you need 2 bits for this. Are you clear? So if these 2 bits are 0, 0, port A is in mode 0. If they are 0, 1, port A is in mode 1. If they are 1 anything, whether they are 1, 0 or whether they are 1, 1, either way, port A is in mode 2. Did you understand this? So, suppose I have kept these 2 bits 0, 0. What do you understand? Port A is in mode 0. Yes, say the full thing. Not that the whole 8255 is in mode 0. This is only for port A. Now 2 bits are used to tell the mode of port A, but only 1 bit is used to tell the mode of port B. Why like that? Why only 1 bit? Because yeah, you got it. Nice. Please, I'm happy you're paying attention. Port B has only 2 options. It can either work in mode 0 or mode 1. So since there are only 2 options, 1 bit is enough to decide it. So if this bit is 0, port B is in mode 0. If this bit is 1, port B is in mode 1. Now do me a favor please. Look at the whole command and tell me what do you understand. Come on. This bit is 1, so it indicates it's IO command. Port A is in mode 0. Port B is in mode 0. I repeat, port A is in mode 0. Port B is in mode 0. So what mode did you understand? Yeah, you're intelligent. Come on, what mode did you understand? If port A and port B are in mode 0, it obviously means port C is also in mode 0. Tell me, did you understand this? Now, do you need a bit to tell this? No. That is why there is no bit to decide the mode of port C. The mode of port C is automatically decided once you decide the mode of port A and port B. Only when port A and port B are in mode 0, port C is in mode 0. Otherwise, port C lines are used for doing handshaking. Tell me, did you understand this? So by now, we have finished deciding the mode of all the ports. Tell me, is this clear? We finished deciding their modes. Port A and port B directly and port C indirectly. Now what do we need to decide? Whether it will be an input port or an output port. Now, why do we need to decide this? See, ports are bidirectional, no doubt. But, yeah, they are bidirectional. So you can use the port whenever you want as an input port or as an output port. But you need to inform this to the port. Why? The difference between a port and a data bus. See, on a port you send data. On a data bus also you send data. Then what's the difference? On a data bus, if you send 25, it will come and go. It won't stay. On a port, if you send 25, it will stay. How does it stay? Every port has a latch. Each port internally has a latch. The latch will hold the data. Do you all understand this? Now, is that a good thing? Of course. So what happens? You send something, it stays on the port. On your calculator, you do 2 plus 3, you press is equal to, the answer is 5. The processor calculated the answer. Through a port, it has sent it to the display. Now, should the processor keep sending 5, 5, 5, 5, 5? No, it will send 5 once. Should the 5 come and go? No, it should stay. Who is holding it? The port is holding it. Tell me, did you understand? So if we send something, the latch holds the value because the port has a latch. Now this latch is damn useful when you're using it as an output port. But the same latch becomes a pain when you want to use it as an input port. Why? In an input port, what do you want to do? You want to send data or you want to read? What do you want to read? What you had sent or what someone is sending? Now if you want to read what someone is sending, you have to stop sending first. Your latch has to be disabled so that the port becomes a free line so that somebody can send data to you. So for that you need to inform the port whether you intend to use it as an output port or as an input port. Please tell me, did you understand this? So you need to inform 8255 which port is input, which port is output. That you do individually port wise. So this bit tells the direction of port A. 1 means input, 0 means output. So suppose I keep this bit as 1. That means port A is an input port. Tell me, did you understand this? Similarly, this bit tells the direction of port B. 1 input, 0 output. So again, if I keep this bit 1, that means port B again is an input port. This bit and this bit decide the direction of port C upper and lower respectively. This is for port C upper, this is for port C lower. 1 means input, 0 means output. So suppose I have kept these two bits as 0, the whole port C is output. If I keep them as 1, the whole port C is input. You can obviously even keep them different, making half port C input, half port C output. Nobody does that, but in theory you can. You may be then wondering why have they given it separately. This whole section, if you notice, no, not the color, don't notice the color. This whole section belongs to group A and this whole section belongs to group B. So for the grouping logic, if port A is in mode 1, these lines are used for handshaking. Port C upper is used for handshaking, but still port C lower is free. If port B is in mode 0, port C lower is still free. So you can just decide the direction for port C lower as an input port or as an output port and vice versa. So because of the grouping logic, they've shown it separately, but invariably both these bits will be the same. Either both of them will be 1, that means the whole port C is input, or will be 0 as in the whole port C is output. Now look at this. What has happened? This number formed is 9 and this number is 2. So the whole number becomes 92H. This is your command. What have you achieved? Port A is in mode 0 and is an input port. Do you understand? Port A mode 0 input. Port B is in mode 0 and is an output port. Or input port, I'm sorry. And port C is in mode 0 and is an output port. So what you have managed to do is initialize 8255 as per the specification. Now this is a question that they keep asking different universities. I'm associated with Bombay University, but I see papers of various universities. Students keep calling and asking doubts on WhatsApp from different universities. Many of them have questions like this. So if they give you any specification, you should be able to form the command. All you have to do is, as per the specification, put 1s and 0s. So let's just have a 1 minute recap. This bit is 1 to indicate that it's IO command. These two bits decide the mode of port A. the direction of port A, the direction of port C upper, mode of port B, direction of port B, direction of port C lower. Did you understand? Now once you form the command like 92, this is how you give the command. Move AL, comma 92H, put the command in a register like AL and output it at the address 86. This is how you give it in 8086 if you're using an 8086 processor. If you're using 8085, the instruction will be MVI A, comma 92H and out 83. Over there the address will not be 86, it will be 83. When you learn 8085, you will see it designing, you will come to know why it's 83 and not 86. But for 8086, this is how you give it. Okay, that's about it. So this was your IO command. I hope you understood IO command. Now the next command is BSR, the more interesting one and the more useful one in the real world. This command has massive application in the real world. Look here. BSR, one of the best features of 8255, this feature is only for port C. Now, why is it only for port C? Why have they given such a useful feature only for port C? Look here, there is something very special port C did for us. Look here, this is your 8255. Okay, so this is port A, this is port B, and this is port C. Now, port C has 8 lines, upper and lower. Let's say line number 7, 6, 5, 4, 3, 2, 1, 0. Okay? Now, what do you know? When port A is in mode 1 and port B is also in mode 1, they take away lines of port C for performing handshaking. You know that? So each port takes how many lines of port C? 3. I had told you 4. I know, don't worry. I told you 4 because you would be wondering, if I would have told you that it takes only 3 lines, you'd be wondering what happens to that 4th line, because we say half goes to port A, half goes to port B. So that's what. So after this, the next video that I'm going to make, I'm going to show you handshaking in detail. You'll come to know that to do handshaking, any port requires only 3 lines from port C. It needs 4 lines altogether, but from port C, it takes only 3 lines. The 4th line is already available with 8255. Anyway. So the point is, port A and port B will take 3 lines of port C. Port A will take the higher 3 lines, port B will take the lower 3 lines. Not necessarily the same numbers, I'm just showing as 3 lines. So, do you understand? 2 lines of port C will still be free. What do you want to do with them? Use them or waste them? Of course, use them. How do you use them? By transferring data. So, let's say I take line number 3 and connect something like a bulb or a fan or an air conditioner on this line. Now on this line I can send a 1 or a 0. Okay? By that I can turn this air conditioner on or off. If I send a 1, I turn it on, as an example. If I send a 0, I turn it off. Now to do that, I will be sending data to 8255 and I will be directing it towards port C. The problem is our data is 8-bit data. Excuse me. Our data is 8-bit data. So when you send 8-bit data to port C, you will send something on line number 3, no doubt. But something will also come up on all the other lines. 1, 2, 3, 4, 5, 6, 7, 8. This will go on line number 0, line number 1, line number 2, line number 3. Yes. Depending upon whether you want to send a 0 or 1, you will keep something over here. But there will be other values also which will go out on the other lines. So what will happen? In order to use this one line, you will disturb all the other lines. Do you want to do that? Is that what your intention was? Your idea was, if these lines are busy doing handshaking, why waste these 2 pins? Let's use them also. But in doing that, you don't want to affect the other lines. That means you want a new method, a method by which you don't operate on the whole byte. You operate on a single bit of port C, a single bit to which you will send a 1 or a 0. If you send a 1, you will set that bit. If you send a 0, you will reset that bit. This is called BSR. BSR stands for bit set reset. So BSR is a command It's a command by which the programmer can set or reset a single line of port C without affecting any line, without affecting any other line. These are 8 lines of port C. Imagine you've connected them to 8 different bulbs. You want to turn on this bulb, this one. You have no clue what these bulbs are doing. You can't even see them. You don't want to interfere with them. You want to individually make this line 1 or 0. If this feature was not there, to make any line 0 or 1, you would have to affect the whole port. Till now, we thought you operate on the whole port, which is true for all ports, including port C. But additionally, because of this command called BSR, you can individually make any line of port C 1 or 0 without affecting the others. That's the meaning of bit set reset. You can pinpoint on one bit and individually make it 0 or 1. So what did it suddenly do? It suddenly transformed port C from being one 8-bit port to becoming 8 independent 1-bit ports. Tell me, did you understand this? So what can you do with this? Connect them to 8 tube lights and switch them on one by one without affecting the other. Or connect them to 8 missiles, connect them to 8 showers and fire them one by one. You can do a lot with these lines. In the real world, they have massive application. I hope you understood this. If you connect 8255 to an A to D converter or a D to A converter or a stepper motor or any kind of real world interface, you need to control these lines individually. To make one signal one, you don't want to affect the others. So over there, this feature becomes very handy. Anyway, now let's look at the command and wrap up the video. So this bit is 0 to indicate that it is BSR, because both IO and BSR command are commands, so they both given at the address 86. So to identify that it's BSR, this bit is 0. These 3 bits are don't care, so that's nice. These 3 bits are PC. What are you doing? Come on, it's too obvious. Select the line of port C. You can choose any line out of the 8 lines of port C. It's not necessary that BSR is done only when port A and port B have taken these lines for handshaking. Even if port A and port B are in mode 0, all these 8 lines are free and you can still do BSR on any of these lines. So if you've kept over here 0, 0, 0, that means you're saying you want to operate on line number 0 of port C. 0, 0, 1 means line number 1, blah, 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 all the way up to 1, 1, 1 means line number 7. So suppose I've kept over here 0, 1, 1, that means line number 3. And S/R, so obvious. 1 means set, 0 means reset. So if I've kept this bit 1, I'm saying I want to send a 1 on line number 3. If I keep this bit 0, sending a 0 on line number 3. Sending a 0 on line number 7. Sending a 0 on line number 0. Sending a 1 on line number 1. Please tell me, did you understand? This decides the line number, this decides what you want to send, this decides that it's BSR command, and these 3 bits are don't care. That's your IO and BSR command. I hope you understood all of this. Okay, I'll be putting up more videos as soon as I can. Wish you all the best. Do it.